So whenever we have a function that has a higher degree in the numerator, like x squared minus 1, let's say, divided by x, exactly 1 unit difference. So degree 2 and degree 1, or degree 5 and degree 4, or degree 10 and degree 9. Of course, that's way too much. But as long as the degree of the numerator is exactly by 1 unit higher than the degree of the denominator, this function has no horizontal asymptote, but slant asymptote. What does slant asymptote mean? Okay, this is horizontal, this is vertical, this is slant, or this. It's not vertical, it's not horizontal. It's just a positive slope or a negative slope. Okay, so here's an example. Of course, I will first factor the numerator, because when I set this function equal to 0, only the numerator can be 0 for the function to be 0. So there are two options, x equals 1 and x equals negative 1. So I can get my table started already. And I also know that x cannot be 0. So f prime of x, f of x, and the second derivative. Okay. So negative infinity to infinity, no, not 0. We know that x equals 0 will be a vertical asymptote. And the function is 0 at negative 1 and at 1. The function is 0 at negative 1 and 1. And at this point, I will determine this limit, this limit, this limit, and this limit. And then I can move on to the first derivative. Okay, so I will simplify the function as much as I can. So then f of x, x squared minus 1 over x, because this is one term, I can rewrite it as x squared over x minus 1 over x. Here I will simplify, and I have x minus 1 over x. So now when I determine the limit at negative infinity, I know that this approaches 0. This approaches 0, we know that, at infinity. 1 divided by huge is 0. But then this approaches negative infinity. The same way, the limit as x approaches infinity from x plus 1 over x, I'm sorry, still minus, is infinity. For the same reason. Because this approaches 0, and when x approaches infinity, the whole thing approaches infinity. So I found these limits. I know that this is a vertical asymptote, but that's not sufficient. I have to find the limits. No problem. Limit as x approaches 0 from the left of x squared minus 1 over x, and limit as x approaches 0 from the right of x squared minus 1 over x. When I plug in 0 here, the numerator is in both cases negative. When I plug in 0 from the left, this is negative. So then this must be positive infinity. Okay, 0 from the right, this will be positive. But negative of a positive, this will be negative infinity. So the function is finished. Now I can move on to the first derivative. Very simple, very easy. If I simplify it. So f prime of x prime is 1. Remember, 1 over x prime is negative 1 over x squared with minus in front. Find the least common denominator, x squared plus 1 over x squared. Always greater than 0. Always positive, never 0. Fine, okay. I'm just making sure. We're going to make sure in a second. I was a little bit surprised that we're getting. Okay, so now we have to make sure that this row works well with this row. That's when I catch my mistakes. I see many of you already go directly to the second derivative. Be very careful, because if you make a mistake on the first derivative, the whole thing collapses. So careful with that. I'm not saying that the method is wrong. I'm only saying be very careful. Okay. So from negative infinity to 0 to positive infinity, that's true. That's true. From negative infinity to 0, that's true. From 0 to infinity, that's true too. So now I can find the second derivative. I will use this, not this, to find the second derivative. This is much easier. So this prime is 0. This is x to negative 2. X to negative 2 prime will be negative 2, x to negative 3. So the second derivative is this. When x is negative, the whole thing is positive. Negative here with minus in front. And then when it's positive, when x is positive, the whole thing is negative. So here it holds water, here it does not. Final step, the slant asymptote. But I chose a simple example for you. So the function is x minus 1 over x. This is the slant asymptote. Y equals x. At infinity, this approaches 0. So this is the slant asymptote. How do I graph something like this? So I make myself a note here. Y equals x, slant asymptote. So now I don't need anything else but the table. So let's graph this. When we graph functions with asymptotes, we have to graph the asymptotes first. So there is a vertical asymptote at 0, but this will be an overkill, so I'm just going to write here x equals 0 VA. And how do I graph this? Is a very nice function. It bisects the first and the third quadrants. Y equals x. Okay, so now I just want to do what the table is telling me. From approaching negative infinity, cross at negative 1, 0, and go to positive infinity on the left-hand side of the vertical asymptote. From approaching the slant asymptote, cross at negative 1, 0, and go to positive infinity. On the other side, coming from negative infinity, cross at 1, 0, and approach the slant asymptote. We say asymptotically get closer and closer to the slant asymptote. Okay. And this is the graph of f of x equals x squared minus 1 over x. So if you want to put this in the graphing calculator, you can, of course. We have in y equals, clear anything, and just put in, don't forget parentheses, x squared minus 1, close, over x. But if you do not put y equals x as the second function, as the slant asymptote, the calculator will not graph it. And I'm going to choose the standard viewing window. Here it is. So the function is coming from negative infinity, approaching the slant asymptote, crossing at negative 1, 0. This is not correct. It does not stop here. It goes further away to positive infinity. It's incorrect. It doesn't start here. It goes to negative infinity, crossing at 1, 0, and approaching the slant asymptote, we say asymptotically, closer and closer, closer and closer to the asymptote. So I think that this is too much work for a test or final exam. This was a simple function that I selected. So I'm not going to test you on graphing something like this, but with a slant asymptote. But I will ask potentially, does this function have a slant asymptote? And you'll say yes or no. if the degree here is 5 and the degree here is 1, you will say no, because the difference in degrees has to be exactly 1. The top has to have a degree exactly by 1 unit higher than the degree of the denominator for a function like this to have a slant asymptote. So this completes all the material for test 2. So again, in case you forgot, we have 2.1 through 2.3, and we have 3.1 through 3.9, except 3.7, which we did not cover, the elasticity of demand. Any questions?
And what's the test, Monday or Wednesday?
Monday I still would like to review. And the test is a week from today. What is a week from today? April 6th? Yes. So on Monday, at least half the time, I would like to answer your